Hey guys, so for this chapter, we're going to do 3 different parts. This is part 1. This chapter is acids and bases. You will need out your periodic table. Alright, so just some common things. Acids have been involved in lots of movies and TV shows over the years. And acids are the reason things taste sour. We're going to talk about that more in a little bit. In fact, acids have even been in James Bond movies where he has a pen that's filled with acid and he's able to melt prison bars with the acid. And that does actually do that. Metal will dissolve in an acid. All right, so things you need to know. Acids have a sour taste. They will dissolve those metals and they will turn blue litmus paper red. Now you can see in this image on the right that it was blue. You stick it in the liquid and it turns red. Also remember, y'all can pause this video at any time to write stuff down. All right, so if you recall from when we did naming way back in semester 1, H at the beginning is what indicates that something's an acid. And remember, if it has the prefix hydro, that means no oxygen is involved. These are just going through some common acids. So hydrochloric acid is one of the most used acids in chemistry, I would say. And it's also the main component in our stomach acid. Next types of acids, notice they also both start with H. Sulfuric acid, that's the common acid that's used like for battery acid. So when you see even on your car or on regular little batteries, when they have corrosion, it's from that battery acid. And then nitric acids are commonly in fertilizers, which some people use as explosives. So that's where those are commonly seen in the real world. Acetic acid, again, that H is in the front. That is vinegar. And then carboxylic acid is just a group of acids that all have this one piece. Acetic acid is one of those acids. All right, then some more common acids. Citric acid, y'all should know what citric acid is. That's the acid that is in different kinds of citrus fruits, like especially lemons and limes. And then malic acid is in apples and grapes. Now, when you think about it, green apples are almost always more sour or tart than red apples. That's because they have more malic acid, because that acid is responsible for the sour taste. All right, now we're switching to bases. A base has a bitter taste. Now, normally we don't taste bases because our stomach is acid, so we normally ingest acids. But some things that you may have tasted would have been either coffee or tea, just black coffee or black tea. Those normally have a bitter taste because of that caffeine, or possibly soap. Soap is a base. All different types of cleaning products are bases. Even sometimes when you are eating and you just use hand sanitizer, it's got that kind of bitter taste. That's from that hand sanitizer. Bases will have a slippery feel, and then they will turn red litmus paper to blue when you put them in their liquid. Here's a picture of common bases. Again, most of them are cleaning products, which is good because they're slippery. Also, you'll see some like medications. That's for heartburn, which is caused by too much acid in your stomach. And so if you take a small amount of something that is basic, then it makes your heartburn not as bad. All right, so here's again some common bases. Conene is just an alkaloid. It's often in hemlock, and that's something that is poisonous to us and other animals. And so it's just a plant, and that indicates, hey, by the way, don't eat me because I'm poisonous. And then, like I said, coffee and tea earlier, that's because the caffeine itself is a base, so it's giving off that bitter flavor. These are just other common ones. Sodium hydroxide and potassium hydroxide are the most commonly used ones in lab. Then we've got, they're also used in like petroleum processing and cotton processing. Sodium hydroxide is the active ingredient in Drano that cleans your drains at home. Sodium bicarbonate is baking soda. That's the active ingredient. And it's sometimes in antacids like Tums. And then sodium bicarbonate will neutralize that stomach acid, which will relieve that heartburn or even sometimes that acid reflux, depending on how bad it is. So these are the different definitions you need to know. You're going to need to know the Arrhenius definition. Let me just, because there's going to be a different definition in a little bit. So an Arrhenius acid, this is the most simple definition. That's an acid that produces hydrogen ions in solution. Remember from when we did net ionic equations, if it was aqueous, it breaks apart. So it will produce hydrogen ions in our solution. This slide is just telling you, hey, by the way, when a hydrogen ion comes into the play and it's alone, it'll add to the water because all of these are aqueous, and it'll make this compound, which we call hydronium. Now, hydronium is interchangeable with H plus that's aqueous because that just means it's hydrogen plus by itself in water, which is hydronium. I almost always write H plus because it's shorter, but the book's going to write H3O plus, and I just need you to know they're the same thing. All right, the ionizable hydrogen, the one that comes off, is generally going to be the one at the front when we write the formula. Okay, it is sometimes, see, this one's not the regular formula, it's the structural formula. So it will generally be the one that's attached to the oxygen, though, if you're having a structure. Normally you don't. All right, so these are Arrhenius bases. So this is still that Arrhenius definition. That Arrhenius definition. So an Arrhenius base will produce hydroxide ions in solution. Just remember our polyatomic ions don't break when they go into solution. So this sodium hydroxide breaks into sodium ions and hydroxide ions because they're in an aqueous solution. Now under this definition, the Arrhenius definition, acids and bases will always combine to form water, so they'll neutralize each other, which we're going to talk about in a few minutes. So the next definition is called Bronsted-Lowry. So they were working together, like at the same time, not together in the same place, and they developed a better definition. So this is the Bronsted-Lowry definition of an acid and a base. That says that an acid is a proton donor or a hydrogen ion donor. Now the reason they call this a proton, because H plus means it lost an electron, so it has no electron because it gave it away. A hydrogen doesn't have any neutrons to start with, and then all that's left is a proton. All right. And then a Bronsted-Lowry base is a proton acceptor, so it's going to accept that hydrogen ion that the acid just gave away. And these happen in normally one equation. Okay, there we go. All right, so if we're looking at this, I know none of this is red. We're looking over here, H3O, that came from hydrogen. So this hydrogen gave it away, and the one that's a donator, this is our acid. And the one that is our acceptor is the base. Okay, you definitely need to be able to do that. So here, we're looking at a different equation. And on this side, it's NH4. On this side, it's NH3, which means this hydrogen went over here. So now water is our acid because it gave away the hydrogen. And NH3 is the base because it accepted the hydrogen. All right, we're about to get into conjugates. Now I want to discuss what a conjugate means. They will be later on in the PowerPoint for today's part, but conjugates are only on the reactant side, or sorry, the product side. So they're always going to be on this side are the conjugates, and they go together. So that NH3 was our base, which makes NH4 our conjugate acid. They have to go together always. It's not base and conjugate base that are paired. The way you know they're paired, you're looking for the element that's not hydrogen. So this one is both ends, so those are the pair. The other one, we've got two O's, that's the pair. Okay, so if we were looking in this one, This would be our conjugate acid, which I'm going to abbreviate as Ca. And this would be our conjugate base, because the chlorines are the ones that go together. So you're not paying attention to the hydrogen for the conjugates. You're only looking at the separate piece. All right, so we're going to label them. I'm going to do them bigger so we can see. Okay, so H3O plus HSO4 minus. All right, so this hydrogen moves to the water to make this H3O plus. So this is my acid, this is my base because it accepts it. Now on the other side, the HSO4 goes with the H2SO4. So this is my conjugate base because they go together. Now this one becomes my conjugate acid because the water and the hydronium only change by one hydrogen. Okay, let's do the second one. HCO3 minus plus water here. All right, then we've got our carbonic acid plus our hydroxide. So again, you have to look where the hydrogens are moving. So if you look here and there, the water lost a hydrogen. So now the water is the acid. The carbonic acid is the base. Now the carbonic acid goes, the hydrogen carbonate goes with the carbonic acid. So it's the conjugate, which makes this the base. So then you need to pair them. Okay, there is some practice for this on mastering. If you need more practice, do these ones. All right. We've already talked about that. This one, though, I need you to write down this bullet point. A substance that can act as either an acid or a base is called amphoteric. That's all it means. It can gain a hydrogen or it can lose a hydrogen. That does mean it needs to have a hydrogen. Otherwise, it's not amphoteric because then it can't lose one. I know it's not red, but that's important. If you were confused on the conjugates, you probably need to write this top part, the base plus a hydrogen yields conjugate acid, and the acid minus a hydrogen yields the conjugate base. Okay, again, it's the acid with the conjugate base or the base with the conjugate acid. It has to be different acid-base pairs. They cannot both be a base, and they cannot both be an acid. Also, only one hydrogen moves at a time. Just one. All right, so here's another example. The base accepts a proton and becomes a conjugate acid. So you add a hydrogen, and the acid becomes a proton, or donates a proton and becomes a conjugate base. So you remove that hydrogen. All right, now we're talking about neutralization reactions. What I would write for the neutralization reaction is this part down here at the bottom. Acid plus base yields water plus salt. From here, you need to keep in mind that H plus OH makes water. So what I do to decide what's happening, this H we use it, this OH we use it, and then whatever's left, that makes our salt, which is our KCl. Remember when you're making salts, which are just ionic compounds, the metal always goes first, so you're going to need your periodic table out to be able to write these problems. Now this one does happen to be balanced, but it's not always balanced. You will have to balance them. This is always the net ionic. So if you want to write that down, that is the net ionic for a neutralization reaction where you have an acid plus base. Always the net ionic. Okay, this is just showing some that make gases. That's a gas evolution reaction, if you remember from when we did reactions in chapter 7. All right, so we are going to do one. HCl plus calcium hydroxide. Again, they always make liquid water. And then whatever's left. So I used all of this hydrogen and all of this hydroxide. So left, I have calcium and I have chlorine. This is our reaction. Now, these did tell us they were aqueous. On mastering, they're going to want the states of matter. Water is always liquid, unless it says otherwise. And then, according to your solubility rules, calcium chloride is soluble. If you need to go back to that, that was written chapter 7 as well. Okay, I'm also going to do this one because it's a different number. Oh, you know what though? That one we did was not balanced. So I've got 2 chlorines on the product, so I need to put a 2 here. And now I have 4 because I have 2 hydrogens in HCl, and I have 2 in CaOH, so I need a 2 there. These are actually pretty easy to balance because normally you need 1, 2, and 1, 2 on the other side, or 1, 3 on one side and a 3 on the other side. So let's do this one. H3PO4, aqueous, because it says aqueous, plus NaOH, aqueous, makes water, always, plus whatever's left. So again, OH is gone, H is gone, so I have Na3PO4, and that's also aqueous. If you remember, all group 1 metals are soluble. So now we need to balance. I've got 3 Nas on the product, so I need 3 NaOH there. And then now I have 3 O's that are not part of phosphate, so I need a 3 there to balance that part. All right, if you need practice, there's plenty on mastering. One more thing, again, at the beginning of this part, I told you that acid will dissolve metal. When it does that, it does produce a hydrogen gas. Now, I am not asking you to memorize how to write these equations, but this is just a single replacement reaction where there's a single element on both sides, and they switch spots in the compound. Okay, but I will not ask you to predict these. Now, could you balance it? Absolutely. Same thing with these. I'm not going to ask you to predict these, but this is a double replacement reaction. This is when an acid reacts with a metal oxide, and it produces water and some salt. Again, I will not ask you to have to predict these reactions. So we're going to skip these parts. If you want to look at them, you're more than welcome to. All right, and this is the end. This is just a reaction with a base. Aluminum can react with a base, and it makes something called alum, which we talk about later on. Y'all have a great day.